Hi, my name is Justin Senyk, and I'm a senior in chemical engineering. My research project is a density functional theory study of propane dehydrogenation on nickel-zinc alloys. I completed this study as a member of Dr. Jeff Greeley's research group alongside Ranga Seemakurthi. The primary motivation behind this project is the increasing availability of shale gas in the United States. There are many shale gas deposits in the U.S., and shale gas is expected to account for an increasing proportion of our natural gas production. As more shale gas becomes available, the catalytic dehydrogenation of propane to propylene is becoming more significant. The catalysts that are currently used are generally alloys of palladium or platinum. However, these catalysts suffer from low selectivity, high coke formation, and high cost. Alloying these catalysts with zinc has been shown to increase selectivity and reduce coking, but doesn't address the issue of cost. In this project, we use density functional theory to evaluate nickel-zinc alloys as catalysts for propane dehydrogenation. We accomplish this by analyzing the binding energies of key adsorbates, transition states and activation energies of rate-limiting steps in surface reactions, and the binding energies and transition states of segregated surfaces. The first set of calculations we carried out were the binding energies of key adsorbates. We tested a total of 3 alloys: pure nickel, nickel-3 zinc, and nickel zinc. The binding energies of some key adsorbates relative to pure nickel are shown in the chart. The adsorbates shown were selected because they're good indicators of selectivity and coking. Weaker binding energies for methylidyne, ethylidyne, and propylene indicate that the catalyst should be less likely to coke or form deeply dehydrogenated products. For 1-propyl, a stronger binding energy usually means that the first hydrogen removal in the dehydrogenation reaction may proceed easier. Next to the chart, you can see the results of the activation energy calculations for nickel. We use the nudged elastic band method, which allows us to determine the transition state and activation energy for key reactions. The 3 reactions shown are known to be the rate-limiting steps of important surface reactions. The first reaction is the removal of the first hydrogen from propane to form 1-propyl. The second reaction is the removal of 1 hydrogen from propylene to form 1-propenyl. The final reaction is the breaking of the carbon-carbon bond in propyne. The second and third reactions are unfavorable as they lead to deeply dehydrogenated products and coke formation, so a higher barrier here is desired for these steps. After we calculated the activation energies on pure nickel, we performed the same calculations on nickel-3 zinc and nickel zinc. The main reaction that we're interested in is the breaking of the carbon-carbon bond in propyne because this forms coke and deactivates a catalyst by removing active sites. As you can see in the graph, nickel has the lowest barrier for this reaction, indicating that coke formation may occur at higher rates. Both nickel-3 zinc and nickel zinc show significantly higher barriers for this reaction, indicating that coke formation should be reduced. In the images below the graph, one can see that the transition states are similar on both surfaces. The slightly higher barrier of nickel zinc is likely a result of the fewer overall nickel atoms nearby. As a result of the fewer available nickel sites, nickel zinc has the highest barrier of all the reactions we examined. Therefore, nickel zinc should provide the highest selectivity to propylene and the least amount of coking out of the 3 surfaces we tested. Propane dehydrogenation is usually carried out at high temperatures, which can cause atoms on the catalyst surface to switch positions or segregate. The segregated surfaces for nickel-3 zinc and nickel zinc are shown. Each surface has 1 pair of nickel and zinc atoms in swapped positions. In the case of nickel-3 zinc, the formation of the segregated surface is slightly exothermic. The nickel-zinc surface takes more energy to form, but could definitely form at elevated temperatures. The binding energies of the segregated surfaces relative to the clean surfaces are shown in the chart below the images. The binding energies on nickel-3 zinc are very similar to the clean surface because the surfaces are relatively similar in energy. The binding energies on nickel zinc are much lower than on the clean surface. This is likely due to the cluster of nickel atoms now present on the segregated surface. Surface segregation also impacts reaction barriers. The barrier for propyne carbon-carbon bond breaking on the segregated surfaces is shown. The barriers on the segregated surfaces are significantly lower than on the clean surfaces. In fact, the barriers are more similar to pure nickel than they are to their respective clean surfaces. Again, this is likely due to the cluster of nickel atoms that forms as a result of the segregation. Therefore, surface segregation at high temperatures can result in increased coke formation, even on traditionally more selective catalysts. Further study is needed to determine the degree to which segregation occurs. In summary, we have shown that nickel-zinc alloys show potential for use in propane dehydrogenation. Alloys with higher zinc content exhibit higher selectivity to propylene. However, surface segregation can cause issues that should be investigated further. Additional studies such as microkinetic modeling or experimental testing of these alloys should be conducted to more comprehensively investigate these effects. Thank you.